Welcome to the latest episode of Star Cells and God. My name is Fuz Rana. I'm a biochemist and a Christian apologist, and I'm joined in studio by Dr. Jeff Zweerink, who is an astrophysicist, a Christian apologist, part of the team here at Reasons to Believe, which is the organization that sponsors this program, thanks to the generous gifts and donations of viewers and listeners like you. Today, we're going to be talking about two discoveries that provide evidence for the Christian worldview. Jeff is going to be talking about the improbability of the origin of life, and I'm going to be talking about new insights into the origin of life's biodiversity and how that supports a role for a creator in the history of life. You don't want to miss it. Hey, Jeff, welcome.
Fuzz, how are you doing today?
Good. So you're going to talk a little bit about the improbability of life's origin. So why don't you go ahead and take it away?
Well, yeah, as I was reading through, just kind of looking at the literature as it comes out, and there was this article, it was The Unreasonable Likelihood of Being. It talked about origin of life, terraforming, and AI is what it's in here. And what attracted, or what I found interesting about this article is not that it's like it weighs in and helps me understand origin of life any better, but they're looking at it from a kind of how can we put equations, how can we formalize this more? In some sense, it's like the Drake equation and looking at, explaining our place in the universe. It's not so much that, okay, we've got this equation and therefore now we know how to solve it, but it allows you to kind of categorize what are the pieces of information we have, what don't we have, what could be good, what could be hard here. And that's kind of the flavor of this paper, but I just thought it was interesting in light of kind of this idea that, we can explain everything. We can explain everything using the natural laws of physics. And lo and behold, there are these things that just appear really bizarre or unlikely, or helps us identify where we really don't have good information. And I thought it'd be fun to talk about just because the stuff they talk about, you're going to have more expertise on than I do. So it'll be fun to kind of have a little bit of back and forth there. But I kind of look at it also, you kind of in light of where we find these numbers, often you'll run across, especially when we're talking about design of the universe, the space energy density is fine-tuned to 1 part in 10 to the 120. And it's like, okay, there are these really huge numbers. What does it mean? And what do the scientists actually do? Because what I've found often in the physics part of that, as an apologist, my inclination is to say, oh, this means that it's so unlikely, and that points to a creator. And I think that's a reasonable way. But often, quite honestly, a way a lot of those numbers, it's like, okay, when you come up with these really big numbers, that's a sign that there's something here. We're missing something fundamental. And so, not that it says, okay, that's not an argument for God, but it's like, okay, let's step back and realize where we know things and where we don't. And I think that's kind of the flavor in which I read this article.
Yeah.
And,
So let me ask you this question before you get into it. For the people that are watching the podcast or listening to it, so the question is kind of, so what, right? Why do you think this is really worthwhile delving into from a science faith perspective? I think there's some obvious answers there, but
no, that's a good question. And I would say one is that I think it is important to recognize that there's kind of this narrative that, okay, science is kind of explaining everything. And to just be aware that there are some fundamentally central issues that's not that science hasn't made progress or understood things, but it's like, we really don't understand what's going on here. I think space energy density, the dark energy in our universe, we know it's there. We've got a sense of it, but it's like, what is this? We just don't know. Dark matter's in that class. I think we're closer to understanding dark matter in a fundamental way than space energy density. But, we talk a lot about, in any sort of science faith issue, evolution plays out in there. It's like, oh, evolution, everything makes sense or nothing makes sense except in the light of evolution. Well, if you can't explain how life got here, you can't really claim you've got a naturalistic understanding of things. And so I think it highlights where we know and what we don't know,
right,
so that we can talk more reasonably about things. And hopefully where you're kind of coming at things from as a Christian, I come out with things from a theistic worldview. When I'm talking to someone who comes from a naturalist worldview, we got to have a common language or understand things. I think it highlights that there are some really big things that
Right.
naturalistically we don't understand, but also, hey, how do we dialogue about this where we're actually
Yeah.
being constructive and just saying, oh, you're being unreasonable. Oh, you're just throwing God at the game. There's so many bad ways to have that
Right.
conversation to try and have a good conversation. Those are
Yeah.
kind of the two big things in
Yeah.
my
I
book.
think you're making a good point though, in the idea that we so often just take for a given that science has explained everything,
Right.
or it's well on its way to explaining everything. And you're highlighting the fact that there are some places where science is not even close to being well on
Right.
its way to explaining things. So that really calls for humility,
Hmm.
I think, on everybody's part. But it's very dangerous, as you're pointing out, to point to those places where science doesn't have an
Hmm.
explanation and insert God. We really want to be arguing for God based on positive
Right.
evidence more so than making a negative argument.
Yeah.
Yeah, thanks for that.
Well, and it's interesting too because the Piper, like you said, the unreasonable likelihood of being buried. I'm Robert, I think Endres from the Department of Life Sciences, Imperial College London. And in the abstract, talking about the origin of life, he got the kind of the bottom line that I thought was interesting. Our results highlight the formidable entropic and informational barriers to forming a viable protocell within the available window of Earth's early history. And like I said, none of this is new to you. You've talked about, the origin of life and what is the biochemistry, the geology, what are the conditions there? Do the things that we know that formulate or that produce biomolecules work, and that this is all what he's wrestling with here. But I do think it's interesting that there are formidable entropic and informational barriers. And what's interesting, and or a number of things that I found interesting is that he talks about these all cells come from cells is one of those tenets or
Mhm.
dogmas that are often thrown around. It's like, okay, so where did the first you got to answer which came first, the chicken or the
Right,
egg? And I think it's no sense do I want to imply that scientists haven't thought a lot about this, but there isn't there. My understanding as an astrophysicist is there's just not a good answer for this at this point. That you could kind of the options that are thrown around are, and they reference this in here. Well, improbable things happen in the universe, which is an explanation that's not an explanation at the same
right,
time. There's well, we're just worried about what happened here on Earth, and maybe it was seeded or directed panspermia, which really just kind of shifts the problem off to another place, or stepping back and saying, all right, what are the constraints? What can we do that would help us understand? Are we in the
right.
ballpark, or at least where might we be missing fundamental pieces of the equation here? And what he talks about is like this somewhere else hypothesis. It talks about 2001: A Space Odyssey, where there's this black obelisk that helps the hominins. There's a couple, Star Trek is repeatedly, making life on new planets, and it all happens relatively quickly. But he actually puts in there like at the mother of all terraforming stories, however, is the book of Genesis. I thought that was an interesting way. It was written more than 2,500 years ago. But again, it's this, and he says it's in a somewhat circumspect that this life was created in 6 days. But he goes on. He goes, a claim that is profoundly human thought, if not amenable to scientific testing. And that's is where I think RTB has really put a very unique way, or a very I'll say unique. It's like instead of saying, well, this is just what the Bible says, it's like, okay, how could we go out and investigate this?
Mhm.
And a couple of the things that they brought up in here that are interesting. One is that there's a time scale of having to deal with this, that you have on the early Earth, you've got where the moon forming collision by this body called Theia, that kind of sets a hard limit of you can't get any further back than about 4.5 billion years, because that's when this
Mhm.
object hit. There's another kind of sterilizing event that happened that you might have biochemistry going on before that, but as far as what's going on the earth, you got this hard constraint of it's got to be after that. And then in that so you got the window there that says, okay, that's the beginning of when we can start looking. that you may have contested evidence for early life. They're arguing back as far as maybe 4.2 billion years ago, looking at chemical signatures that then it said, okay, what is the last universal common ancestor? So maybe 4.2, which may give you 350, maybe 400 million years. Or you've got kind of undisputed evidence for fossilized is not quite the right word, of fossil or primitive life 3.5 billion years ago. So you either have 300 million to maybe 950 million, something like that. And then they also there's that. Let's put the time window what it is there, and that's. So I'll say this in the context of all of these. These aren't meant to be, okay, here's the definitive thing, but it's like, here's the case we can make for this. And so as we get more information, we can refine that. But so you got this time window, they're going to argue of 500 million years, just kind of the average or a reasonable average of those two. And then you ask the question, okay, how much information do you have to assemble in that time? And I'll get to that in a second. And then there's the path by which you go about assembling it. And I kind of want to focus on that. How much information do you assemble and the path in which you assemble it? Because what they recognized is that it's not just, okay, we've got the genetic information. They say, hey, what's the simplest life form we know of? I think it's a mycoplasmia. Oh, I'm going to forget the
Genitalia.
That very well could be it. Yeah. Where it's like something on the order of 10 to the 6, 10 to the or 10 to the 5, 10 to the 6 bits of information there. They said that's actually the smaller amount, because beyond that, there's also the structural information that goes into that, because it's not just do you have the information, but there's information and how it all folds and comes together. And they give an estimate for that. But then you also have the dynamic information, which says kind of, okay, you've got the information in the code of information. How does the code get executed? How does it all play out? And so they used AI and various models of the folding. I think they use AlphaGo AlphaFold for the protein folding. Say this is something on the order of 10 to the 8 bits, because it's roughly, so many gigabytes of data to store the code. Similarly, for models of how the cell works, something on the order of that. So they say you come down, your genetic information is 10 to the 6 bits. The total information is probably something 10 to the 9. And so that gives you got to get this much information in place in this time window. And that says, okay, about 2 bits a second is what you have, which doesn't sound like a tremendous lot. But again, it's not that here's the final answer, but given what we know, these are good approximations of that. The part that I think that was the most startling to me in that is, one, it seemed like the amount of information was a little small. The time window, yeah, that makes sense. But then when they were starting to say, how do you get there? So if you say, all right, I got to get 2 bits a year, I think, for, if you got 500 million years and you got to get 1 billion bits, it takes about 2 bits a year. That's not really, that doesn't seem like a lot. But what they were saying now is you got to realize it's not just like you add 2 bits, because there's all of this is done in the context of there's the amount of entropy, or the amount of chemical information that we got from meteorites that were landing on the Earth, and you have to look at it in the context of the protocell and how much information could diffuse in and out of there, not just over the vast oceans, if you will. But then there's this other question of how long, you've got that information, it assembles a little bit. How long does that information stick around? And that to me was one of the bigger features in there, because if you've got various biomolecules that'll stick around for days or weeks, which is not unreasonable, but now you're in an atmosphere where there's no ozone, because there's no free oxygen in the early Earth when we're talking about here. So now you got a lot of ultraviolet radiation that's coming in. Presumably this is in the shallow pools of the Earth, wouldn't apply to deep ocean vents, so these are the variables that they're playing with. But you're likely to have things be destroyed on the order of days or seconds, if you will. And the calculation that I thought it was just worth reading is that if your persistence time, how long the memory sticks around, is something on the order of a second, which is, kind of a reasonable assumption, the wait time for assembling a cell becomes 10 to the 24 years, which is a little bit longer than it's like a trillion times, 100 trillion universes stacked end to end. But even if you extend it out to a persistence time of a year, you still end up with something that's about 10 to the 17 years, which is 10 million times the universe's current age. And so whatever the process is that is responsible for life's origin, those processes have to be able to not only accumulate information, but keep that information around almost for something on the scale of the time of the universe, or at least the whole time that this 500 million years, which is when the protocell needs to get around. And that to me seems to be the biggest place where I can say, all right, 500 million years, that's a reasonable amount of time. You've got 10 to the 6 bits, 10 to the 7, 10 to the 8, 10 to the 9 bits of information, 2 bits per second. That's not unreasonable. Keeping that around for that long a period of time, that seems to be one of those places where we really don't understand what could do this. But nonetheless, I find this whole discussion just really interesting. And so I'll kind of throw it to you. I mean, in this discussion, you think they're on track here? It seems like it's reasonable, but
Yeah, I mean, hearing your description of the work, I think it is quite reasonable in terms of their conclusion that, you've got to accumulate quite a bit of information, over a relatively short period of time, and there's got to be mechanisms in place that cause that information to persist.
mm-hmm.
Something that I think is missing from this analysis is that, one of the things that you absolutely have to have a living entity is the capacity for replication.
Mm-hmm.
And when you look at even the simplest cell, most of that information in a simple cell is devoted to supporting the replication process, or
Right.
is either directly involved or is indirectly involved by supporting it. And so we know that the simplest cell, as you're describing, has a significant amount of information. I always think of it in terms of number of genes, not bits.
Right.
But you're looking at about 400 genes, and this is an organism that can't exist independently.
Meaning,
It can't. It requires growth in a laboratory under highly specified conditions where nutrients are being provided for it, versus organisms that can live independently, where they're able to generate their
okay.
their own source of nutrients.
Okay, so if you take genitalia mycoplasma or mycoplasma genitalia, that would just put it out in the environment.
And it's it. That's it.
So it's got to have other life around it that can allow
Right.
it to live.
It's an
Okay,
obligatory parasite.
gotcha. I see what you're
So what it's giving you is the basic minimum
saying. Mm-hmm.
information that you need for life to exist. But if it's going to be independent life, now you're looking at a chemoautotroph or a photoautotroph. And now the number of genes goes from about 400 to, 1,400 for a chemoautotroph. And if it's a photoautotroph, now you're looking at 2,300.
Mm-hmm.
So, the order of complexity is dramatically magnified to
Right.
think about independent existing organisms. But even when you're talking about the capacity for replication, it's not only you have to replicate, but you have to be able to produce proteins, because the proteins are what is actually the machinery that's replicating the
Mm-hmm.
DNA. You have to have a boundary if it's going to be a cell,
Right.
and that requires active synthetic mechanisms to produce the components and maintain that boundary. And you're going to have some mechanism to extract energy from the environment. But you
Mm-hmm.
can't have a protocell where you only have some of those systems available. They have to all be existing coincidentally. So this is a
Right.
kind of an issue that Michael Behe described as irreducible complexity. I like to call it integrated complexity because you've got these individual systems that are irreducibly complex that have to be integrated. So, in other
Mhm.
words, you could envision that information being accrued in a stepwise manner.
Right.
And I think that's all well and good for that type of an analysis that he's engaged in because he's not talking in specific details.
Mhm.
But I think the problem is even more severe because it's not just stepwise accumulation of that information. It really has to be information that comes together simultaneously. So that,
Yeah. Well, so that was actually one of these questions or a thought that plays in my mind is, okay, so we know, roughly what the original chemical environment might have looked like. We've got meteorites, or at least some measure of that. And then you also know at some measure what the early or what the simplest protocell might have looked like.
yeah,
Now, I think both of those are open to refinement. I think, if I get what you're describing, it may be, so we're looking at this one organism that is the simplest life that we could reproduce. The question of is that the earliest life that could survive on its own is it
yeah,
may be more complex. But this is what I love about these sorts of calculations is it's not here's the final answer, but now someone could come in and say, just as you did, oh, that's not actually the simplest. It's actually got to be more complex because of X, Y, and Z. And now you can have this very vibrant scientific discussion
mhm,
of what's going on there. Now, I just want to restrict and say, all right, we know this is roughly the original environment. We know we got to get to here. Whether it's this particular organism, whether it's
mm,
something that has
right,
phototaxis, whatever it is, if you've got to go from 0 bits or, these minimal set of bits up to let's just keep it at the 10 to the 9, a billion bits. It does seem you could have this occasional, slow, steady walk through there. Or it seems more likely what would happen is you'd almost need to have some cliff ledges where, okay, yeah, we're scaling, moving through this impossible domain, but every now and again something dramatic happens where there's this large increase and you kind of get this stability where you can remain there. From an origin of life perspective, given what you've known and looked, I have this suspicion that the origin of life probably has this hypernatural component to it. In that, if I were to sit there and look at it, I'm like, oh, that's what happened. But there's also a very much, I'm like, I don't see why that ever would have happened. It
yeah,
seems contrived, if you will.
right.
In terms of this, there's got to be places to step. Do you see something like that, or is it more you kind of have to get it all or nothing? Because it does seem to
Yeah,
me you could have replicating things where, okay,
yeah,
it'll replicate. It's not where you're going, but in the process of that, now you've got this ledge
right,
where you could get to the next ledge.
right. And the concept of persistence, I think, is really very important, and I
Hmm.
appreciate that the author of this paper emphasized the need for persistence. The way living organisms achieve persistence is you have active mechanisms that are turning molecules over inside the cell.
Right,
So you don't have a cell where the molecules are static, but they're constantly being formed and destroyed and
right.
formed and destroyed. So it's a steady state, but it's an dynamic system.
Hmm.
And and then you have replication. Replication is how you attain persistence in life.
Right.
And so what he's looking for, and origin of life researchers are looking for, are chemical analogs to what living systems do.
Hmm.
And I just don't know, where you're going to find that. Yeah, you could envision maybe things replicating, and that could create some kind of persistence. Uh, but you've got to have at the same time some way to contain that system. It can't.
Hmm.
So you've got to have a boundary. You've got to have material flowing into that system that's available. Uh, if you're going to have any kind of replication going on. So I just don't know how you attain persistence. Things that tend to be persistent in chemical systems are highly inert. They don't react. And so
Right. Yeah.
you can't have life with inert chemistry. It's got to be
Mhm.
there's this balance between stability for the molecules, but reactivity so that they are able to undergo chemical operations that are needed to sustain life. So, it,
That's actually very interesting because I just know in my investigations into artificial intelligence is there seem to be these things where kind of the general idea is like if we can do this, then that'll be intelligence. And we figured out how to play chess, and it's like, okay, no, that's not intelligence. And then even I think we're at least closer to confusing people with the large language models that are out there. But even what the large language models are doing, they're not doing what you and I are doing. They can produce strings of what we would argue as coherent sentences, but they're not coherent. There's nothing about the AI that's saying, this is a string of coherent sentences. It's actually just really input and output. And so even though it has this appearance of intelligence, the mechanism by which it's doing it is very different. I kind of get there's a parallel with what you're talking about life. You can do things where you get stability or long-term things, but it's very different than what life is doing, if you
yep,
will. And so there seems to be a question of not just can we get stability, but does it apply? Is it stability that can be translated into life? And that also strikes me as a relatively challenging thing to
right,
even understand in the first place.
right. Well, and it seems to me that what this, author is doing is he's thinking about things in very general terms,
Yes.
right? Which so to me, it's not my comments are not meant to undermine
Mhm.
his analysis. It's more, yes, what you're presenting is the minimum problem,
Right.
right? Or the minimum barrier, not,
Mhm.
not the if we can overcome this, we explain the origin of life.
Right. Well, no, I really appreciate that because what there's two parts of this that I thought were interesting. One is there are still some very big unknowns in how do we explain life here? If we can't explain how it started, it's good that you got the maybe have this process later, but to say, oh, we've got a naturalistic
Yeah.
explanation is lacking there. But then there's this second part of, and I just resonate or think about a step. Mother of all terraforming storm is written 2000. It declares that life was created in 6 days, a claim that has profoundly shaped human thought, if not amenable to scientific testing. And so the question I have in there is, as Christians, we think, okay, God's involved in this, I've at least met other Christians, that there's this somewhere between God did something that may be beyond the laws of physics to make it happen to God worked within the laws of physics. And so in that in that question of saying, okay, God's involved here, what does it look like? The more I know what the problems are, now I might be able to say, given what I know of God or given what I've studied through scripture, what are the mechanisms that God might have used or might have produced? And now I can take I think God's involved in the origin of life from being a generic statement to, if God's involved in the origin of life, here's how it might have played out. And we can go investigate it scientifically, which now Christianity is part of the scientific solution, if you will, instead of being perceived as oh, you're just saying God did it, let's not investigate. And I think that has been a hallmark of how RTB has thought about things. And
Yeah.
so that was just kind of this intriguing part to me as the non-expert who really doesn't understand the intimate details. I love the back and forth, but
Yeah.
seems like there's this great opportunity for Christianity to use this to engage better.
Yeah, I wrote a chapter for a book. I think it's called Dialogues on Science and Faith.
Hmm.
It was published by a South African publisher,
Okay.
an academic work. You can actually access it online for free. You
All
can,
right.
if somebody wants to download the entire book. But my chapter was on uh, theistic and non-theistic perspectives on the origin of life.
Okay.
And what I argued in there is that look, the origin of life appears to be miraculous, right? That
Hmm.
it really does look like it's divine design. And I point out to the very point that you're making, which is, um, yes, the origin of life appears to be miraculous, and most people in the scientific community are going to push back hard against that because it seems to be a science showstopper.
Mhm.
That when you say, "Hey, God did it, He intervened in a supernatural, miraculous way," there's nothing for us to investigate. So therefore, we can't entertain that idea scientifically.
Right.
But if you're able to formulate the possibilities of how God may have
Mhm.
engaged through divine action that involve hypernaturalism or uh, something like a molecular version of process structuralism, you now actually have ways to investigate the origin of life, even if it is miraculous. And so, my point is that it's possible to frame this question in such a way that it opens up dialogue
Mhm.
between regarding the origin of life between theists and non-theists, where
Right.
there are productive avenues that we could pursue an investigation, even if we do think the origin of life is miraculous.
Well, it seems like also a cool consequence of that sort of dialogue interaction, at least over time. I don't know what the time scale is, whether it's probably not days or certainly not days, maybe it's years, it may be decades, but I could make an argument about in cosmology. I think part of why the evidence is so strong for the fine tuning and the beginning of the universe is because of how actively people have investigated other ways that don't need to have that there. It's not that they just threw up their heads and said, "Oh, it looks like a beginning, we'll walk away." It's like, "No, what about this? What about this? What about this?" Well, this gives a way for someone who thinks God's involved in there to not only just say, "Well, here's a way that God might not have been involved," but here are some possible avenues that might be. But the more we know about what's going on in there, I think the evidence for
Right,
divine causation is going to grow stronger because we know more,
right.
not because we don't know what's going on here.
Yeah. Well, when it comes to the origin of life, I mean, this is something that it is plainly evident to me by reading the origin of life literature, is there's nothing within the laws of physics and chemistry that make the origin of life through chemical evolution fundamentally impossible.
Right.
I mean, the processes that you need, physical and chemical, exist
Hmm.
to, in principle, produce, through chemical evolution, the very first cells. The problem is um, that we don't have any clue how they would work together to do that. This is essentially the
Right.
point of this
Yes.
paper.
Hmm.
But what I see a lot of times is people conflate the fact that, well, we've got these clues or we've got these potential mechanisms that can account for particular steps in the origin of life, but it doesn't mean that those steps actually will be productive,
Hmm.
right, towards the origin of life, right?
Right.
And that's where I think the real strength of the argument comes into play. It's like, yes, we've investigated for 75 years
Hmm.
possible, chemical mechanisms and physical mechanisms, and we've identified a lot of them, but we can't really show that they operate under the conditions of the early Earth in a productive way,
Right.
or that, and there's other problems that are not taken into account, like this issue of persistence.
Right. It's interesting because one final comment I'll make is that this discussion of the origin of life has a parallel, and it may be a weak parallel, but nonetheless it connected in my mind. Is that one of the fundamental requirements for life in our universe is that there's more matter than antimatter. And what's interesting is that the vast majority of the laws of physics operate with a symmetry that don't allow for that. And your idea of your comment about there being clues that we can explain. So there's some sort of asymmetry in some law that allows more matter than antimatter to be produced. And so eventually all the matter and antimatter annihilate, and there's a little bit of leftover matter, and that's all the stuff we see of the universe. It's kind of a bizarre to think that what we see is the leftovers of all of that. But putting that aside, as physicists have been investigating this, and to my I mean, they've been investigating this for decades now. And there are little places where it's like, oh, there's this one that violates this parity, or this one violates parity, and they found clues to it, but they still don't have a solution to it. And so it's not like there's been just a great joy in trying to figure out what it is, even in the frustration
Mm.
of not having solved it. Now, one distinction here is that everybody expects that there's going to be some physical mechanism that does this. It's not like God just said, well, here, I'm going to
Mm.
split it off. It's not sure exactly what my comment is there, but it's like there's something about, your comment about, I don't think there's anything in the laws of physics that would preclude life from coming about. In the same way, I expect that when we find this, we're like, oh, okay, that's what it is, but it'll still have this signature of something that's remarkable, something special. And I think it'd be fun to actually know, hey, this we could actually explain the origin of life, and it's like, yeah, that's a really cool
Right.
mechanism that God used there. So
Yeah, I think if there ever is ultimately an explanation for the origin of life, it's going to be deeply teleological.
yeah,
It's going to be
right.
deeply purpose driven, and I think that's where things are headed.
Yeah, it'll be interesting to see whether that happens in my lifetime. I think you'll probably enjoy that more than I will, but it'd still be fun to watch. So,
Yeah,
I've just enjoyed. Hopefully that's helpful. Just kind of, I found it a very good perspective on how to just generally think about this without having to be
right,
intimately involved and know all of the details of
right.
protein folding. So,
Yeah, yeah. That was a lot of fun, Jeff. Thanks. Okay, well, to kind of transition to the next discovery, I know that you like explosions,
very much so.
so I'm going to talk about explosions in life's history. But I thought to have a little bit of fun, maybe macabre fun, right? Where you're getting close to Halloween. Uh, we could talk about some famous explosions in U.S. history.
Okay,
So I got three of them
I'm
here.
curious which ones you chose here. So.
You might have a longer list than me, but one of them happened in 1983 in Benton, Tennessee, and it was called the Benton fireworks explosion. And apparently, somebody had a illegal fireworks operation
Okay,
on a farm near Benton, Tennessee, and the police obviously didn't know anything about it
right.
until, unfortunately, it exploded.
Okay.
The facility exploded, and then they realized, oh, there's an illegal fireworks operation going on under our noses. But
Actually, I
unfortunately,
think there was an illegal firework.
yeah, that's right. Yeah, problem solved. But yeah, unfortunately, 11 people died and
Ooh,
one person was injured. But apparently, this explosion could be heard and felt 20 miles
oh
away.
my goodness. Okay.
All right, so the next couple are even more dramatic. One of them happened in 1944 here in California at the Port Chicago facility, and this was a ship called the SSEA Bryan that
Okay.
was a munitions ship that was
Alright.
carrying munitions
Ooh,
into the Pacific Theater for support of the operations in during World War II. And this particular ship exploded
okay.
in the port, killing 320 people and injuring 390 people.
Okay.
So that was,
Yeah, I could imagine that would be
and then another one happened shortly thereafter in 1947 in Texas City, and there was a ship called, oh goodness, I can't read my own writing, but it was essentially carrying 2,300 pounds of ammonium nitrate,
oh, no.
and it exploded, and it ended up um, triggering other chain reactions of explosions in the port,
Ooh,
including another ship that had 1,000 tons of ammonia nitrate. So this was actually quite a disaster. 600 people were killed and 3,500 people
mhm,
were injured. So, when it comes to explosions, we oftentimes think of them as being rather disastrous,
mhm.
right? But it turns out there are also explosions that paleontologists are very interested in that have happened in life's history. These are sometimes called radiation events
Okay.
or Big Bang events,
Right.
where there is this over a very short period of time, this very rapid increase in biodiversity. And so some well-known examples would be things like the Cambrian
Mm-hmm.
explosion. There are these radiation events that happen with fish in the
Mm-hmm.
Ordovician. There are radiation events for reptiles,
Right.
3 for birds, and 1 for mammals. And
I,
so,
I I have to say, I find it odd that we use the term explosion. I mean, very clearly equivocating there in what an explosion means. But how did we get to where explosion, which is almost always destructive? I can't think of too many constructive explosions,
yeah,
but that's exactly what we're talking about, are these explosions that are
yes,
constructive.
yeah,
It's an odd juxtaposition of
yes,
language there.
yeah, it is, it is. But these explosions in life's history are good because
Mhm.
they have accounted for major innovations and moments of dramatic increases in biodiversity.
Right.
And one of the big questions on the table is, how frequent do these radiation events take place? How important are they in terms of shaping the biodiversity that we see on Earth
Mhm.
today? And so there was a couple of researchers, one from the University of Arizona, one from UC Riverside, who published a paper in Frontiers in Ecology and Evolution that basically determined that most of the species that are alive today reflect these radiation events or these explosive instances of dramatic increase in biodiversity, including land plants and animals.
Are most of these radiation events, are they, you mentioned the Cambrian explosion and a couple others, are they all kind of in that time frame, or are they from the Cambrian explosion dispersed up till
Yeah,
today, or
throughout life's history.
okay.
Yeah, these are happening throughout life's history. But this idea that every time there's innovation or a dramatic increase in biodiversity that happens explosively is consistent with our creation model for life's
Mhm.
history, where we would see God's involvement in such a way that we would expect as a signature for creation these sudden appearances, these dramatic
Mhm.
uh, creation events or dramatic events that are characterized by biological innovation in life's history.
You made a statement that most of the species alive today, you may have said all, I don't remember, are reflective of these radiation events or these explosion events. Is 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 that is that an equivalent statement to this kind of just slow gradual evolution that you see, that that's not the way things happen, that things happen explosively
Right,
almost exclusively?
right. I mean, the two models that they're considering in broad brush terms is that biodiversity accumulates slowly over significant periods of time through this gradual,
Mhm.
stepwise evolutionary process versus something akin to punctuated equilibrium where you see stasis punctuated by these
Mhm.
dramatic events of biological innovation
Mhm.
or growth in biodiversity. So those are the two models that they're engaging in.
Sorry, I can't help but make the connection back to our discussion about life's origin, that if that's the way life has developed, it would seem to me the place to go look as not how could you slowly accumulate information through there, but what sorts of things might explosively,
Yeah,
because that seems to be the
yeah,
signature, if you will. That
yeah,
would be the signature of the creator there.
yeah, yeah.
All right, sorry, go ahead.
Yeah, well, I mean, and before we get into it, I think it's worth just asking the so what
Yeah.
question. Why should people spend time listening to this discovery? And to me, I think it's very similar to the points that you made earlier, and that is, you know, um, there's this perception in biology that evolution can explain everything,
Hmm.
and therefore a creator isn't necessary, right? And in fact, I held that view when I was a agnostic as an undergraduate student. And I know a lot of people who see things in those terms.
Right.
So I think it's important that we're able to show either evolution isn't sufficient to explain everything we see, or that the patterns that we see are consistent with a
Hmm.
creator's involvement,
Right.
in life's history. And if a creator is involved in life's history, that's what Scripture teaches.
Yes.
So we become confident in the message of Scripture. But it also means that if there really is a creator that orchestrated life's history, it means that we can ask the question, then why did the creator create us as human beings?
Right. No.
Right. And that's ultimately the heart of the gospel. So, these things are, important, I think, to spend time thinking about.
Right. No, I would agree. That's
Yeah. And then, something else too that I think, by way of just some background for people that are not familiar with reasons to believe, maybe this is their first time encountering this podcast, we hold to what's called an old earth creationist position at Reasons to Believe. So we see the days as periods of time. So we see Genesis 1, well, really all the creation accounts, but Genesis 1 as being a history. So we see it historically, but we just see days as periods of time, not 24 hours.
right.
And so when we look at Genesis 1, and this is going to be important when we unpack some of the apologetics implications, it's a sequence of events that are, I would argue, are more or less chronological, where what we're presented with is a snapshot of what God has done, right? It's
Yeah.
not
Okay.
the full exhaustive description, but these are snapshots that would have been meaningful to the first people that would have received the Genesis 1 creation account. So there's a lot of things going on that are invisible to us based on what we see in Scripture that we get the delight of discovering through science.
Right.
And so our creation model is, one where we see God intervening in life's history to bring about creative purposes. And as, again, I mentioned, we would expect evidence for that to be, again, these explosive appearances. And it's interesting when you look at the fifth day of creation, where God commands the waters to teem with life. That seems to describe kind of an explosive appearance
Right.
of life forms. And that's the type of thing we see with the Cambrian. So anyway, in terms of this particular study, so what these researchers did to address the question is actually a fairly comprehensive analysis of 5 different databases that reflected different aspects of biodiversity. So, for example, they looked at a database that involved 300,000 species of land plants that included 10 phyla, 140 orders, and 678 families. They looked at
Are these all things that exist today, or is this
Yes.
stuff in the fossil record?
No, this is stuff that
Okay, this
exists
is all
today.
stuff that exists today. Okay.
Yeah. And they were looking at animals in general, and they included 1.5 million species, 28 phyla, 1,710 families. They looked at about 1 million species of insects, 31 orders, 870 families, and then vertebrates, which included 66,000 species, 12 classes. And then they looked at a database that included 2 million species, covering 17 kingdoms and 2,545 families. So each one of those databases represented an individual analysis.
Right. So just because I'm not sure what those numbers mean. Is that a pretty substantial fraction of what we know? Is it like 10%?
Yeah, right.
Where are we in that?
Well, I mean, this would be a substantial fraction of what we are familiar with
Okay.
in terms of land plants, animals, insects, vertebrates,
all right.
that type of thing. They didn't do anything in their study involving microorganisms.
Oh,
That's
okay.
just way too involved. So these are essentially complex multicellular organisms that
all right.
they're dealing with in their studies. And what they discovered is that radiations are characteristic for all the different levels of biological classification hierarchies. You see radiation events. But what they noted is that most of the biodiversity at a particular level is usually due to a single clade or group or a couple of them that have extensive biodiversity, where all the other groups basically show very limited biodiversity. So the biodiversity, so for example, with land plants, most of the biodiversity is in a single clade. Even though there's a number of different groups, There's
Okay.
a single one where almost all of the 80% of the biodiversity is found. So it's
Interesting.
and so what they argued is that from an evolutionary perspective, probably what's happening in life's history is that there are these key biological innovations that take place that then open up new niches
Mhm.
for these organisms, and they very rapidly diversify to fill those niches.
Okay.
But that in that it's usually an innovation happening in a single group that's driving that biodiversity. So for example, with the Cambrian explosion, what you're looking at is in very broad terms a transition from single-celled organisms to complex multicellular organisms.
Okay.
And because of that innovation, that now leads to opening up a large number of new niches that are then very rapidly going to be filled. Or when you go from aquatic
S s
organisms,
so if I understand that, it's like, you've got a kind of single-celled organisms or, a variety of single-celled organisms, and then something happens and, with the Cambrian explosion, you've got large multicellular organisms.
right,
This group over here somewhat becomes largely static, and this is where all the diversity happens.
right,
And so somewhere in the Cambrian explosion, there's going to be a group
right,
that and that's where all the diversity comes with everything else
right,
somewhat static.
right.
That's the basic idea here.
Yes,
Okay.
yeah, yeah. Or when you go transition from an aquatic organism to terrestrial organisms
Mhm.
for the first time, now there's all these new niches that are going to very rapidly be filled. So they're arguing this seems to be, based on what we observe today, this seems to be the pattern in life's history.
Mhm.
Now, uh, you know, my contention would be that on the surface, that explanation from an evolutionary perspective is all well and good, right? Hey, there's new innovation
Mhm.
and it happens explosively. But when we start thinking about what these innovations entail, where it's such a dramatic, you're introducing such dramatic biological novelty that it's going to give that organism an advantage and it's going to allow for this very rapid appearance of biodiversity, requires unbelievable amounts of uh, highly integrated systems emerging all at once.
Okay.
Because when you talk about, like, let's talk about the transition from single-celled organisms, or what we might even call colonial aggregates. They are in effect single-celled organisms that are just aggregated together
Mhm.
as colonies. That versus organisms that have fully formed organ systems that are highly integrated,
Right.
right? That have appendages, visual systems, that type of thing. You're going to have to introduce, all these these gene
Mhm.
networks to encode all of these biological traits. There, you also have to develop or have to institute a developmental regime where things are going from single-celled
Mhm.
organisms to fully formed adult individuals. This requires extensive amount of information that has to be highly integrated in order
Right.
for these systems to emerge. So it's all well and good to say, oh, innovation led to opportunities for rapid biodiversification. But what is required for that innovation to take place? It's similar to what
Mhm.
you were describing with the origin of life. There's a whole lot of information that has
Mhm.
to be introduced. And it's not just genetic information, but it's structural information or algorithmic information. It's a highly dynamic system,
Right. Yeah.
where that information has to be managed in terms of when is it utilized, when is it expressed, when is it shut down, in order for, biological traits to emerge that are novel. So,
Mhm.
I mean, so on one hand, you could say, well, the fact that this is rare, is an attests by the fact that, these are very complex
Mhm.
processes that have to take place, you know, um, or it just simply a creator steps in and is creating all of this apparatus that then allows for that innovation to take place
Mhm.
and is also playing a role in that rapid diversification.
So it's I mean, your description is I've been listening to your describing what's going on here, and there's there's part of this is like, yeah, well, that's what the evolutionists say. That's the way it played out. And, because there is, it seems to me to make good sense where, okay, there's a group of creatures that can operate in this environment, and it's somewhat new, that there's a rapid innovation. To see a whole lot more stuff of that play out, that kind of makes sense to me. It's like
Yeah. Well,
it really doesn't seem that hard to envision.
right.
Correct?
Yes, you are correct, and I would agree with that. That there's for an evolutionary biologist, there is, this is a nice, neat story. Hey, there's innovation that happens, but it becomes close to basically hand waving because you're not explaining how that innovation could actually take place.
Right. That's what and listening to your description, it's like, for the lack of a better, it's the miracle happens here, and then you've got all that. It's like, okay, this is all fine and dandy after this, but it seems like this is saying, okay, yes, we've got this story that once the innovation takes place, explaining this
Correct.
is not so bizarre, but you do also have to account for and this takes place, and that's
Yes.
a really big step, kind of like with life. I mean, it's like
Yeah.
once you get cells, everything
Right.
happens, but you have to include getting cells in the first place.
Well, and it's a very easy. I mean, this would be analogous to put this in the context of what you discussed with the
Mhm.
origin of life. Oh, we could say, look, there are chemicals that formed on the early Earth, and they began to complexify and aggregate
Mhm.
into these protocellular entities that over time acquired a capacity for, you know, crude metabolism and some capacity for self-replication.
Right.
And then over time, this was refined, and that led to, the origin of life, or the last universal
Mhm.
common ancestor, right? That's a nice, neat story that is compelling at some level,
Right.
right? Particularly then when you can say, well, here's a study where, somebody made amino acids and somebody made nucleobases,
Right.
right? But then but when you actually sit down and roll up your sleeves and think through what actually has to happen, that's when you begin to realize there's so many things that have to come into
Mhm.
existence. Again, where each biological trait is formed through a network of genes that are interacting,
Right.
and each gene is involved in, you know, dictating different biological traits.
Mhm.
So there's a very complex network that has to somehow emerge, and you need to specify, all the gene interactions and the timing of those gene interactions
Right.
in the just right way to developmentally produce that biological trait that's somehow producing that innovation. This is not something that is going to accrue through some kind of stepwise process.
Right.
This has to be, instantiated all at once.
Well, and that's what, I mean, I'll refer back to it, but this idea that there's the genetic information, the structural information, and the dynamic information in there. If you just have to worry about the genetic information, this all seems a lot more plausible because, okay, occasional mutations, particularly bad environment. Yeah, this is largely destructive, but I could envision a bunch of mutations that allow all those genes to be there. But you now also have to make sure that all of those things that happen structurally play together, and you have to execute them. That becomes a lot harder picture to maintain. And if I get what you're saying, that's what you're talking about here, is that yes, there's this large increase in innovation, but that innovation is very difficult to explain just and you can't just say, oh, here's a couple of pieces. It's like there's a it's like saying I'm going to change a race car into a tractor. In principle, none of those are hard changes, or they're all straightforward changes, but it's a lot of engineering to make it happen
Right.
because this is so finely tuned here and this is so finely tuned here to get there. There's a lot of engineering in there, and
Yeah.
these innovations show the signature of having a lot of engineering to them.
Yes. That's a great way of
Okay.
putting it. Um, yeah, and a lot of times what I see evolutionary biologists do is say, look, we could have gene duplication, and that
Mhm.
creates, more genetic information that can be
Mhm.
shaped to create new biological systems. But that again negates the fact that you have this highly fine-tuned system where even subtle changes in gene regulation create catastrophes,
Hmm.
developmental catastrophes. So you've got to have not just new information, but it's got to be integrated, with other genes to create these novel features,
Hmm.
and again, it's through time, through the developmental process. This is
Right. Yeah.
just, extremely difficult to envision how something like this would happen from an evolutionary perspective. But yet,
Hmm.
again, this is exactly the type of signature I would expect to see if there's a creator that's involved.
Right.
And again, this is something that we could study
Hmm.
hypernaturally,
Right.
right? Where we could say, well, we know how to manipulate the genetic information in organisms and create novel features. It's very, very hard to do. Could this be the mechanism that the creator used?
Hmm.
So there may be ways to study this, but as we get into the details, I think we're going to realize these are highly improbable events, left on their own
Right.
through some kind of unguided materialistic process, that there needs to be, oversight,
Hmm.
intelligent oversight.
Well, and it almost seems like the better we understand that, maybe I'm connecting something that shouldn't, but yeah, you made a comment about how cells are a dynamic system. It's not like there's just this supply of stuff and it maintains that. There's this dynamic nature too. So having it seems like there's got to be something in that dynamic system that actually works against things changing.
Yes.
So not only you've got to have the change introduced, but you've got to have the replication system accommodate that
Mhm.
change as opposed to filtering it out. By understanding those things better, that might actually help us understand the big steps and how they might have occurred or what the
Right.
limitation. It's like the better we understand it, the more we see how
Yeah.
elegant it is, if you
Yes.
will. So,
Yeah, I agree. And then one final point, and I don't want to go overboard making this point,
mhm.
but it's very interesting in light of what they think is happening in life's history, where there's just really a few groups or clades that are responsible for most of the biodiversity, and that they looked at, land plants and animals and vertebrates, right,
Okay.
insects, is that when you look at the Genesis 1 creation account, you see, for example, on the fifth day, on the third day, God introducing plants on the land.
Right.
The fifth day, there's a very general description of the birds in the air, in the creatures in the sea.
Right.
You know, on the sixth day, animals on the land.
Right.
So it's a very, it's very easy to criticize the Genesis 1 account. I've heard some skeptics do this. Why isn't there more detail there? Why isn't there more mention of all
Mhm.
these different life forms that we see throughout Earth's history?
Right.
Well, this makes sense in light of this study, because if birds, for example, are one of these clades where you're
Okay.
going to have this massive biodiversification, you just need to describe the origin of that dominant
Gotcha.
clade or group that's going to, again, account for most of the biodiversity that we see.
Right.
When it comes to vertebrates, we just need to describe the fact that they're animals on the land, and
Right. Yeah.
there's a very few number of groups that account for all that biodiversity. So anyway, it's just an interesting observation. I wouldn't want to push it very hard at all.
No, that's fair. I just, in the discussions, the paper I talked about and the paper you talked about, it does remind me just of an interaction I had with my dad. And, you mentioned punctuated equilibrium earlier, that back in the 80s or 90s where this was coming out, it was having a discussion with a group of students that I was a student involved with, and had a chance to go see Stephen Gould and didn't, but we're talking about his ideas. And I remember kind of describing the ideas to my dad, and his comment was, that looks a lot like creation. And I think that thought has guided me a lot, that I don't, not to get so hung up on the words, but what are you actually describing? And you may be using a different set of words for it, but it looks a lot like creation here. So,
Yeah. Yeah. Well, and that's a great way to summarize this. It looks like a whole lot like creation.
right.
So, well, thank you so much for joining us on this episode of Star Cells and God. We would love for you to take part in the discussion. Use the comments to let us know what you think about what we discussed today. And then also, make sure you go to our YouTube channel, Reasons to Believe, and subscribe and use the notification button so that you are alerted when the next episode of Star Cells and God drops, which is every Wednesday. You can also access Star Cells and God through your favorite podcast app. Remember to like this video, to share it with a friend, and the more that we know about science, the more that we have reasons to believe.